something called Rydberg atoms, and this is their special thing is that this is why it can entangle. So if you want to look more into Rydberg atoms, you should. In a nutshell, you have atom A sitting close to atom B. Atom A becomes excited, and because it's close to atom B, it takes some of the energy from atom A and it phase shifts the energy of atom B. But that means that atom B can't be excited by the same laser because it's not in the same frequency. And by doing this, they become codependent. And then, because they are correlated physically, they're now no longer being able to be described independently, which that actually means entanglement. So you take atom A and atom B, even after it's been excited, they're still entangled. So they're back in the ground state, they're being moved apart, however, stay entangled. And then you have a row of atoms on the left, a row of atoms on the right, and one of them is being preserved and the other is being read out. So far, so good? Okay, cool.
Can you add us to the Zoom meeting?
Oh, sorry. Yes. Okay. Oh. Yes, it's called the Rydberg atom, and in this case is rubidium.
And then just share your screen.
Yep. Cool. Is it online?
That's good.
Cool. Awesome.
I have a question.
Yes.
I heard that once when you read this, when you try to read the state, it changes the something there's something when you read it and then it changes
That's right.
It seems like she's right on to get into that part, right?
Yeah, so I don't want to go too deeply into it because there's many layers of this. So there's logical qubits, there's ancillas, so that you'll read some of them and some of them are entangled with other ones, some of them are for storage, some of them are for data, and I don't want to confuse anybody.
Okay.
But the point here I'm trying to make is that it's basically they get entangled, they're moved in different places, and their states are together. So they're entangled. So what is a QPU? Is a quantum processing unit, which are these arrays of atoms that are being trapped with a laser. And the laser is actually moving the atoms around in the QPU and making this lattice. And it's not only trapping the atom, but it's also bringing down the temperature to microkelvin, which is super cool. And if I learned anything in molecular dynamics simulations, that anything below that breaks the simulation. So you literally can't go colder than that. So atom shuttling is what I'm trying to explain here, is that you take, please come in, there's more space. And people are on the doors, so please come in. And, yeah. Thank you. So this is directly from Quera's YouTube, and it looks just like this. These are atoms. And they're being moved around with lasers, and by moving them around, they're getting entangled. And so far, so good? Cool.
I have one question.
Yes.
Is there a specific distance that you separate them, or maximum distance?
Yes, good question. There is a specific distance. Of course, you can't get too close, can't be too far. I will need to look up the exact distance. But yeah.
So when I hear lattice, I think of the post-quantum algorithm, the MLKEM.
Yeah.
Is that based off this lattice structure?
So lattice, I think, is a word for things in a row. So in this case, it's a lattice of atoms because they're in a row. So they're separate.
The post-quantum cryptography scheme is mathematical lattice. So in high-dimensional space, you just find the closest point to another point throughout a special lattice structure.
Oh, okay.
We can talk about it afterwards if you want.
Yeah, cool. All right. And so how are these atoms being shuttled? It's something called a spatial light modulator. So it's a laser that splits up the light into, again, a kind of matrix. And this is controlled electronically, along with something called an acousto-optic deflector, which further modulates the lasers with sound waves. And these are the two main technologies that are doing the atom control. So you move many rows of atoms at the same time with an SLM, can excite individual atoms, and you can also move atoms to do the entanglement as well. And this is controlled actually with gates and circuits. So how everybody's heard about quantum circuits and gates, right? It's really confusing stuff. But what does it mean is that you, over a certain amount of time, you perform these gates, these operations that are physical, and this is how you design a quantum circuit. And I think that this is where agents could come in. So you have a set of parameters, you have a row of events, and agents could be trained into making the design and the control of a QPU. So you take some code, you build your quantum circuit, you compile it into voltages, which controls the SLM and the AOD, which are doing the atoms, moving the atoms. So what is the readout of the QPU? Does anybody have an idea? Yes?
Is it a probability?
Well, you collapse a state, so because things are in superposition, once you read it out, you collapse a state and you get the probability distribution of the final state. Yes. Any other ideas? What is the readout of a QPU? In this particular computer, it's actually a camera. So they take a picture of the atoms, and so the qubits are projected into 0 or 1 based on what the image is telling us. And this has become some computer vision problem. And so machine learning is applied on the fluorescent image of the QPU. This is literally how the information is being read out from the quantum computer. So my idea here is, okay, VLMs could do some of this work and analysis of the QPU readout, and therefore agents. So far, so good. Okay, so if you ask me, if I put quantum and AI in a blender and I ask, will it blend? I think yes. And this is a topic that I've been really interested in for a while. It's called optical neural networks. And it's a chip that you can use optical information, so light encoded data, and propagate through the chip, and it works as a perceptron. And this actually came out of a lab here at MIT from Dirk England. And the companies like Light Matter and Lightelligence spun out from this paper. So an optical perceptron, you take a lot of information, you reduce the dimensionality, and you basically convolve. And the main technology here is that you have light propagating on one channel, or a waveguide splits into two. You phase modulate one side, they come back together. And when you do this, it's a linear operation, so adding, subtracting, dividing, multiplying. And so you train the parameter of the phase shifter similarly as you would train a weight in a digital neural network. And once you have data in the optical domain, you're not consuming any power. So it's actually quite cool. And you can parallelize light speed operations once you're in the optical domain. So this technology was really interesting for me because it's very effective for linear operations, but there's room for innovation to do nonlinear activation functions. So our idea was, let's put this on telecoms. So the internet, the data is moving optically over the world, then it becomes electronic, and then it gets processed classically. So we thought, okay, let's put an optical neural network in between, offload some of the compute, and reduce the amount of digital compute needed to do neural networks. And the idea was to replace servers with huge chips. However, we don't need to reinvent the telecoms wheel, but quantum wheel is literally being invented. So my pitch to you is, can optical neural networks be useful in quantum computing? Yes. And so we go to some more terminology. So co-packaged optics is where you take photonics, so guiding light on a chip, and electronics, and you put it in the same package. So you put an optical neural network on one side and the chip, a normal chip, like a GPU chip, on the other. And so on the material, so the material is called the high electro-optic material, meaning it can conduct light and electricity equally, or with capacity. And so the idea here was, let's put co-packaged optical neural networks on telecoms. The data is already optical. You can train the phase shifters, and the readout would be optical as well. However, I thought, okay, maybe they can be also applied on cold atoms. So actually, because light can propagate bidirectionally, and it can also be modulated with something like an integrated spatial light modulator or a liquid crystal displays, which diffracts light. And also the phase shifters themselves can control light. So not only doing the readout optically through the chip, but also manipulating the atoms. So that's one pitch I have for you. The other one is, can we actually have the atoms trapped onto chip and have a high electro-optic material, which again conducts electricity and light pretty efficiently? And it turns out this is happening. So this paper came out from here as well, from co-founders of Clara and again Dirk England. And what they're trying to do is actually these traps where they put the atoms in and they do an MCI mesh, which is the same technology I just described, to do the readout of the quantum computer. So instead of a picture, it would be physically placing the atom on the chip. So far, so good? Any questions?
Yes. Yes. So this is amazing stuff. But so I'm an IT guy. I deal with a lot of errors. Whenever there's errors, there needs to be error correction. And I'm wondering, with any error correction, it feels like the correction would break the entanglement that we just established.
So I didn't cover this not to confuse people, but it's also a very difficult topic to kind of understand as a beginner.
Oh, okay.
So, but I think that there's always error. You know, we are in a chaotic world.
Yeah.
It's only about that's why it's called fault tolerant. So we tolerate error. Like, can we use statistics and can we use math? Can we have math on our side to be sure that most of it is correct? And so, yes, that's on the algorithmic side. You have quantum error correction, and that means in the control. So there are many more steps. So I'm very very simple, high level talk today. Yeah. Okay. So another idea that comes to mind. Okay, what about we put an agent or an AI on chip? So, of course, you have a co-packaged optical chip where you can have the agent live on the electronics and do the control of the QPU. Or you could have a stack of chips and have a cluster essentially do the control of the atoms. And this would be an agentic co-packaged neural network controlled quantum computer. So what I covered today is AI where? In the circuit design, on edge, or as an agentic orchestrator. And this idea actually was proposed to us at our quantum cafe that we did in Berlin with one of NVIDIA's scientists, where he works on a different platform, but essentially performing quantum experiments get so complicated that he thought AI could be applied. And this is in our YouTube channel, which you can join. Yeah, go ahead. So this will be recorded also on YouTube. So thank you.
Yeah, I missed it the first time too.
Okay.
Thank you.
Sure. So thank you. Yeah. So I've been working on this in entrepreneurship, looking into photonics and optical neural networks in collaboration with the plan was to collaborate with IBM, Fraunhofer, and a spin out here in Boston, and which led to me creating this platform of bringing scientists together with venture capital. Why? I think that science belongs to everyone, but science becomes useful when it meets a market. So I found a laser neuron trying to bring together scientists, doing workshops, panels, hacks, to facilitate the transition of science into applied things. So we started in Berlin. So far we've done 2 events called Quantum Cafe. And this is my team based in Berlin, and we have support from German government institutions and Berlin Quantum, LEAP, and Optech WB. And here in Boston, we have support from Sunday and Ethos, and this is our 3rd event so far. Over here, I'm looking for people who want to get on board and help us organize stuff. This is a QR code to our website and my email, in case you'd like to get involved. And thank you. And then, yeah, there will be more events. We also have a Luma calendar. I will be sharing this on our website. And now is the time for questions. So thank you so much.
I have a question. For the optical neural network part you mentioned, there was like a part where you like reduced the power.
Yeah.
Is that like part of like an experimental thing you're trying to do, or does it just like use less power, and if so, would that provide like more like sustainable
So yeah, so okay, so we use power in creating light and modulating light, but once light has information and it's traveling, it doesn't need any power. It's coherent. It's moving in one direction. It's moving really fast. And the idea is that this would reduce the power consumption of moving data around in data centers. And that's what they're doing in light matter and light intelligence and the interconnect market. So moving data around is quite big. But optical neural networks for me is an optical computing. So can you use the chip and do a convolution and computation on chip? Yeah. I'd be happy to take more questions. I think are you ready to go?
Yeah, could you let me share my screen?
Yeah, sure.
That way-
Okay, all right. And so now we have Andrew, and also Arthur, Natella. So thank you for being here.
So I sent a request on yours. Until then, so my hack, briefly, just a high-level overview. We're going to go a little bit more into the details of what is quantum mechanics, a little bit. We're going to talk about vectors and linear algebra, just a little bit, in probability space. That's kind of where we're going to ground the hack in the beginning, and then we're going to take you all the way to building a quantum k-nearest neighbors, or a quantum KNN algorithm, at a very conceptual level. Don't have enough time to get into Q-skip code, but we can talk about resources on that right afterwards.
Okay.
All right, so let's see.
It'd be cool if you had a cat.
Be cool if I wish I had a Schrodinger's cat slide. So I decided to kind of forego a little bit of like the slides for Schrodinger's cat and just kind of give an overview for the things that I should expect pop science to have explored a little bit for the sake of time. We'll see. Maybe I'll regret that, but
So we're
we'll
not
try.
seeing your screen, we're seeing your...
We're seeing nothing. Okay, let me try that one more time.
I think full screen doesn't work very well with sharing.
Alright, I'm gonna stop sharing and then I'm gonna go and try that one more time. And if not, that's gonna be some sort of crazy issue. Alright, share. Boom. Boom. How's it looking? It's looking great. Thank you. Alright, so this is the block sphere, and this is a neural network. We're doing the whole thing with the blender that she talked about. So this is a little bit about what we're doing today. We're talking about quantum uncertainty and superposition. Moving on to classical learning. That's my background. I'm Andrew, by the way. Classical learning, I work on continual learning. Then we move away from classical learning for a moment and we talk about Grover's algorithm. Grover's algorithm is a search algorithm. And we'll get into some fun misconceptions about what Grover's algorithm might do and what quantum mechanics can provide. Afterwards, we'll talk about quantum learning, which is what you're all here for. And then we'll see one example of what quantum learning might look like in a quantum KNN. All right, let's get to it. All right, so quantum uncertainty. So when you hear about quantum uncertainty, you normally think of superpositions. You know, you are a cat and you're either dead or alive and nobody knows yet. So you should be both dead and alive. And that we call that a superposition of different states. So the states are the outcomes, dead and alive. And the superposition is the fact that we can have a vector or a direction in this space that is between dead and alive. And therefore, you could be a little bit dead and a little bit alive. And then when we observe you, you become 100% dead or 100% alive. That's the observation principle. And I talked about it as if it was the Copenhagen interpretation. These are just words, and we can talk more about them right afterwards. But quantum computers work very similar to classical computers. Those of us that have a STEM background might have seen this. This is binary. I wrote it as an array to keep them separate and also to highlight some notations in quantum computing. But this is just a series of ones and zeros, and that's how a machine thinks, right? Well, quantum computers can think in the same way. This is just a bunch of ones and zeros. These are our final states, dead or alive or some other kind of state. The number 16, in this case, this is like 20-something. However, this is where our uncertainty. we have this ket notation, and that just shows that we're working in quantum space, and this is a final state, not a vector, because this is one of our lovely basis states. It's all 0, 0, 1, 0, 0, 1, or whatever. So this is how we should think about it. This is our basis states: dead, alive, eating tacos, and 1, 1 could be like eating burritos, I suppose. But I guess you would have to be dead and eating burritos, but whatever, or alive. Anyway, this green line, this is our vector that we can do computations on. So in the beginning, our electron is definitely either spinning or not spinning. We can observe the electron in the beginning. So let's say it's aligned with 1, 0. We take an operation, because we're living in a wonderful vector space, we can do a little rotation here. And we rotate it into a superposition of all of our possible basis vectors. This is called a Hadamard operation. We can get into what the different operations mean afterwards. They don't really matter that much for this conversation, but essentially, all of a sudden, we can't look at it. No peaking anymore, because right when we peak, it comes back up. And this is the whole quantum fault tolerance stuff that was talked about earlier with Isabella's talk. We really want to make sure that we don't peak, and it's actually very easy to accidentally peak at something. It's called quantum decoherence. All right, here's a game. So I just talked for a while. I need a rest. So after this, we're going to have a little quiz, so pay attention. All right, so find 42 is very similar to something from a 3 blue, 1 brown video, which if you notice a lot of manum up there, it's because a lot of this was just pulled from a video. Find 42 is a change on that. It's basically, I want to find the number 42. You give me a bunch of numbers, you tell me how many numbers you're going to give me, and I have to find 42. If you're in a classical computer, you run a little bit of code. This is Python. I'll walk you through it line by line. It's not that much. So the function is find 42. You have 120 possible places in your array. We know for sure that 42 is in there, and we know for sure that it's only in there once. That's what I'm telling you about this. So our computer goes in and it says, okay, for every single one of our possible values, if it's 42, if our value is 42, forget the +1, it's array shenanigans, because computer scientists have to be special. If we find it, we print done and we return. We're just done, we halted. All right? And so that's all our function is doing. How long will that take in numbers of queries? I've got a question here.
Yeah, I was wondering, could we structure the data set before we search?
We absolutely can't, because that's more operations, and it's also cheating a little bit.
Okay.
And we can only verify. So I'm only talking about here with quantum computing. This highlights an important thing. We can't. Well, a lot of times we can't ask, is it less than or greater than something else? Instead, because that ends up asking a lot of questions, really. Instead, we have to, and we can classically sort things and be clever about it, but for the moment, I'm only talking about the regime where, like in RSA, we know that when we get the answer, we can verify that it's correct, but when we don't have the answer, we can also verify that it's not correct. So these are verifiable problems, not necessarily non-verifiable problems, like less than or equal to. They ask a lot of questions when you ask them over a whole set. In this case, the question that we're asking is this. Is our number, yeah, this is literally counting every single number. Feasibly, you could pass an array in as well. Is our number exactly equal to 42? And it prints done. All right? So it's asking, generally, in worst case, it has to ask all n questions. You have to go all the way through the list. Best case, ask the first question. On average, you're asking about 1/2 n questions. And in big O notation, that's just n. All right. Does everybody understand find 42?
Yeah.
Excellent. All right, now, in what runtime do you expect a quantum computer to complete find 42? Based on what you know so far about quantum computing from pop science.
I would expect it to be the square root of it.
Okay.
Anyone else?
Maybe the last one.
Oh,
Big
well,
O
like-
of 1.
I don't know. I'm kind of thrown off because like, what if he gets lucky and it's like 50%?
that's usually what it would be if it's 42, right?
If it has to check every single one, it's n. If it can do all of them in parallel, it's 1. If it has to do some sort of shenanigans, it's in between. The idea is if we can do it in constant time, meaning no matter how large n is, we can throw them all in parallel, you would think big O of 1. If you have to do it, guess and check every single one at a time, that's big O of n. Something in between is special. Who knows? Do you have an answer? Oh, you were.
Oh.
I suppose one because I think it should be very fast. Otherwise, we wouldn't be researching it. Right?
You think it should be parallel? A lot of people talk about it like that. Yeah, that makes sense.
Okay.
Alrighty. Well, so the answer actually ends up being the square root of n, and we're going to get there as to why. It is a very, very popular misconception, big O of n. This is actually a famous question that was asked. Almost everybody said big O of 1. Because when you think about it, you think of quantum computing being able to do everything in parallel. And I talked about how each of these is a component of a vector. You only have to ask one question of the vector to change all of its components. So really, it should be big O of 1. Well, why is it big O of the square root of n? We'll find out. All right, but first we're going to take a detour into learning. Learning is all about finding relationships in data. That's what I do every day. That's what I'm doing right now when I'm trying to talk to you guys. I'm paying attention, seeing who's not paying attention. If I'm losing you all or if you all start to sleep, I have to change how I'm interacting with you all. That's what I'm doing. I'm learning, building relationships out of the data that I understand. Okay, a special learning algorithm that Netflix wants to use is KNN. So if you want to give a group of users recommendations based on other users in your database, you could classify these users into separate groups. You could say, okay, this is the group of the sporties, this is the group of the people that want to watch drama and romance, and then these are the group of the people that only want to watch action movies. Okay? If you want to find a new person and ask, okay, what group does this new customer belong to? You have to find a way to take the distance between all of the people in this space and take the k shortest distances, or the k nearest neighbors, and say, okay, what percentage of them belong to each group, and the largest group that's representative of their neighbors is the class that I'm going to put them in. So in this case, our question mark in k equals 3 would be assigned to group green triangle, right? Because it's closest to the green triangle. Does everybody follow that? KNNs? You just learned like 6 weeks of learning class. All right, this is the algorithm. This takes a distance, and this is just the dot product in itself. It's like a cosine similarity. You're just asking how far away is our data point from the training data point that we're on. And we do this for I data points or every single data point in our set.
It sounds like this a correlation thing. Is it like a quantum correlation?
Right now we're just talking about
Yeah.
k nearest neighbor, the
Well-
algorithm.
Yeah,
Not like quantum yet.
this is just regular k nearest neighbors, but exactly correlation, and we'll talk about what that means in terms of quantum in 1 second.
Okay.
All right, so we're back onto the hypersphere. We get to talk about each of these things as if they're a different dimension of our data, and each of these things as an encoding of our data set. So this is like person 1, person 2, person 3, and this is like Rockstar movie number 1, Rockstar movie number 2, anime number 3 or something. Okay? So now we go into Grover's algorithm really quickly. So I tell you about rotations, right? This is our lovely vector that represents our user. And this is our lovely vector representing our guess for find 42. Let's start with find 42. And this is the number 42. If we want to find 42, we can verify everything. Notice that this is a plane along 42. Our dimension is 120. We have a 120 dimensional sphere, which is ridiculous to even think about. but this is one slice of that sphere along the orthogonal, or along the pointed direction of our lovely key value of 42. Okay? So we can rotate it in one orthogonal direction that we stay consistent, and then we have this. And then, as we talked about before, because this is a vector space, we can rotate it over our old vector as well. We can just make the vector again using the same set of operations, and we flip it over it. And then notice how it kind of jumps around using those two operations back to back. These are just rotations in vector space. And now all of a sudden, it's pointed along our line of yellow. And remember, these are probabilities. So this right now is pretty much equal between a lot of different bases, but this is definitely gonna resolve our key, or almost certainly. So now when we take a peek, we're gonna get our answer. We're gonna get 42. So how many iterations did we have to do? How many times does our line have to jump around until we get the number 42? That's math, and it's advanced, and it'll take a second. But if you want to take a picture of this slide for your interest, this down here is the explanation for why we get pi divided by 4 square root of n. That's how many times we have to rotate our vector in space to do it. And down here, along with that slide just before, will help you understand why that is. It has to do with the sum of the squares being the final probability. Basically, the sum of the squares have to add to 1 to have every possibility being 100%. Okay? Quantum learning. We're getting there. Why do we want to do quantum learning? We either want it as an accuracy or a speed up. We either want to be more accurate by using something like a better sampler, or by starting with quantum states, so we can do quantum computing on quantum values, or we want it as a speed up. We want to talk about the speed up because that's what everybody's here for. We want to run fast, right? Do I have everybody so far?
Yes.
All right. Because now this is the quantum KNN. All right, remember, our KNN takes a group, a neighborhood, and says, what percentage of your neighbors are of each group, okay? So we run through some assumptions. We have an x-axis and a y-axis in our data space, and we have a label, okay? This is what a probable data point might look like. So P looks like this. This white is the label. This is one dimension, and this is another dimension. In our hypersphere, we say, okay, this is our point P, and this is some sort of dimension in our data space. This is another dimension in our data space. So really, in our data space here, we have 9 bits, so we have 9 to the power of 2 different little pointers here, okay? So we have a very, very large sphere. Now we take distances between each of our points in our sphere. So going here, we have, this is our target sphere. We also have a lot of data spheres, data vectors in our sphere. So we have a bunch of vectors. We take the closest point between the closest k vectors to our new target vector. So we put all of our vectors in the vector space, and we just take the distances between all of them. The best thing about quantum mechanics in this case is that we don't actually have to do distance. We have to do something called fidelity. So we take the inner product implicitly by just putting them all next to each other. So imagine, I don't have a great visualization for this, but imagine you have 70 red vectors here. Those are our data vectors, and our one blue vector. What we can do is we can rotate the whole vector space so that our red vector is perfectly aligned to the top. We know to sample from the top. We can when we resolve our quantum system, we know that the thing that's closest to the top is probably closest to our vector. So we only need to do one rotation for all of the vectors in our vector space. We sample without sampling our target vector. So our target vector gets decoherent and thrown away. The rest of our vectors, because that's 100% observed, so we can observe that one. The rest of our vectors, we just sample that same state. We ask, okay, who's got right spin now? And the vectors that have right spin were most likely our nearest neighbors. So it's really not necessarily, it doesn't necessarily have to be k nearest neighbors, but it could be p nearest neighbors. We take k out of the p, or the greatest number in our p nearest neighbors that actually got selected, and we can say, okay, are they all green? Are they all red? Let's find out. And then of course, you do have to normalize by the amount of data that you have. Because now we're sampling from the top, and we're asking, okay, how many of them are in this state? We could have all of them in that state, but that wouldn't give us that much information. We have to be surprised. So that's where the math comes from the distance. We take one sample at a time by weighted similarity. Over time, we can get those p. If they all end up being like one rotation, you have to sample again. So again, we're finding that we can make it more helpful for us if we do more rotations, or in this case, more sampling. But in the beginning, we get a little bit of information. In the same way, when we were talking about Grover's algorithm, if you sampled right now, you actually are more likely to get our lovely key than you are to get anything else. But we don't want to sample yet because you're still not quite guaranteed. Well, you're never truly guaranteed, but you're not at 99% accuracy. So you have to, in this case, sample k times p times, okay? Rather than k to the p. So you are getting a bit of a speed up here with quantum mechanics. All right, and that is actually, I think, all of the talk. Let me just end it on some, okay, I have 2 more slides, and then I'll get to your questions. Useful resources, take a picture of this page. This is how I learned a lot of this stuff. This is super helpful. You have like full implementations of KNNs, and quantum KNNs. You have learning materials for all of this stuff. The final sampling for quantum KNNs, honestly to me, it feels, if you know what Bayesian inference is, it feels very much like if you treat it as a Bayesian inference problem, you can be much more successful than if you treat it like a classical KNN.
Well, wait, how do you update your posterior if it will just collapse when you update it?
So that's a good question. In this case, you might actually have to put a lot of instantiations of your data. Again, we have this like accuracy, memory, speed trade-off that we have to make with everything, and quantum computing is not exempt. So in this case, in the case that you're talking about, we want to have more samples. So the memory is going to increase. So we need a lot more logical qubits in order to make that realistic. Or you have to take a lot more actions. So if you want it to be a traditional k-nearest neighbors and actually have good fidelity and only sample once, you have to do a bunch of rotations in order to really separate your vector space nice and neatly, which is easy to do in high dimensional space. High dimensional space, everything's very far apart. So.
I guess I'm wondering, like, for folks that aren't maybe as interested in, like, improving speed or performance, but interpretability, would this approach still make sense? Like, for example, if you're, like, I'm more in the neuro space. It's like, for example, if you have, like, vision data, we would maybe, like, train a vision model and then go, like, layer by layer to kind of interpret what's happening. But would you, like, I don't know, decompose the quantum circuits, or would you like look at like the like how would you kind of make interpretations?
It's a good question. So at first, like the first algorithms or the first computational problems were like, let's find the optimum of this problem. Let's do an optimization problem, which are easy to check and verify. So this is where it started. I think now it's gone a bit further and there's more complexity, but really just trying out problems you can verify easily and work with them better.
And statistical verification is the key here. We don't, just like with a neural network, and actually even worse than the neural network, there isn't real traceability here. A lot of craziness can happen. And this is only exempting quantum decoherence and error correction and all of that, assuming it runs perfectly. There's still probabilities. As I showed with Grover's algorithm, that's a perfect case, and that we're still only getting at 98% feedback rate of actually getting our key. And there's not really a feasible algorithm to close that gap to 100.
And so
That's what you miss. And so everything, one second.
Sorry.
So everything that we do has a certain amount of uncertainty. And I mean, even in a classical computer, you could get a ray of sunshine, like a photon interfering with your computer. So interpretability is going to be generally hard, especially when we're working in only probability space. But if we do things over and over and over again, we get enough fidelity that we can rely on it. And that is the purpose of even thinking about quantum computing. A lot of machine learning actually relies on probabilities. So working in this space is helpful, even though certainty kind of goes away.
So I'm familiar with the kind of optimization approximate of k-nearest neighbors of HNSW, the hierarchical navigable small world where you put it into a graph, and that's how vector databases work.
Right.
It's like a cosine similarity
Yes.
metric. And so given the overhead and uncertainty or errors that emerge from the quantum process, where is the actual advantage over the approximation that's fast?
The fact that we can rotate the whole vector space is an advantage. So with the hierarchical small world, that is a very clever way to look through as many possibilities as you can and still get good feedback, good fidelity. But you still have to ask order of n or order of log n or something, different questions depending on how you organize the database. Well-organized databases, you have to ask less questions. Less organized databases, you have to ask more questions. In this case, you have to ask one question. You just rotate the database. When you sample k, that's when it starts to become difficult with the fidelity. You have to trade the amount of questions you ask with the amount of times that you have to sample. And so k nearest neighbors might end up being a misnomer. K nearest neighbors might not win. It might be kp nearest neighbors, where p is the amount of samples that you have to take of k things in order to get an actually quantum stable or statistically stable and statistically sound output. Any final questions before we jump to? Yeah. All right.
For the quantum KNN algorithm, is the complexity for the number of vector rotations? Will you always have to do that regardless of the distance function? Let's say we didn't use a Euclidean distance, we use some other distance function. Is there anything clever you can do with a distance function to optimize the complexity? Or is it just kind of
The clever thing that you can do with the distance function is just take fidelity as your distance, which asks no questions. If you wanted to do other distances, actually translate it into Euclidean or Manhattan distances, what you would have to do is you would actually have to warp your state space or warp your probability space. And that ends up being on some order of log n, depending on how many transformations you have to do. Because again, you have to make that stable and high fidelity as well. So generally, I just see the inner product implementation because that's just so simple, and you only have to ask one question. The swap operation is all you have to do.
But there's no way to shrink the number of rotations.
From one to anything else, probably not. Yeah. If you wanted to increase the number of rotations in order to decrease the amount of times you have to sample, you could do something clever like that. But I don't know of an algorithm that does that.
We can continue the discussion later. We have one more speaker. Thank you so much.
Thank you all.
Okay, Arthur, feel free to share your slides. I'm just going to check the volumes here. Okay.
Yes.
So Arthur here is going to talk about jobs in quantum. So if you're interested in getting a job in the quantum space,
and also career coaching agency.
Maybe you get a little bit closer to the mic,
Oh.
and then yeah, people can also move closer. It's a little bit. It's as loud as it can go. So.
Yep. All right. So hopefully you all can hear me. Actually, let me see if I can turn my audio up a little bit more. Can you hear me okay now? Ish.
A bit closer.
A little bit more. I'm gonna do the grandparents. Where do I push the power button thing? But all right. So I'm gonna get really up here. Can you somewhat hear me now? Okay. So we're gonna talk about careers in quantum. So the first thing I want to talk about is that there has been massive investments in quantum computing. The Department of Commerce, this is a clip from a headline, Department of Commerce announced letters of support, really a commitment for $2 billion to accelerate quantum computing in the United States. There's a lot of talk right now about where will jobs go, fear of AI taking jobs. And I can say with utmost certainty that jobs that intersect with generative AI, specifically LLMs, will not be replaced. And this is even more so not be replaced for the foreseeable future. And I'm very confident about that. In quantum computing, that's even more so for a lot of what we're going to be covering today. So if we're talking about a job that you are interested in and that is in many ways future-proof, quantum computing is going to be a place for you. And I'm very excited to talk about pathways into quantum computing for us and how you can get in there. So I know we did talk a lot today about quantum computing, but even though we did talk a lot about what it is and what it is not, you may even still be going, all right, we're going to talk about quantum, but I still don't really know what a quantum computer is, and I'm a little bit afraid to ask. I'm going to go through an oversimplistic explanation of what quantum computing is, just for foundation setting, even though we've talked about it a few times today. And I'm also going to talk about as not just what is quantum computing. I'm going to talk about some myths. So what are some myths that are propagated about quantum and how who is in quantum? I'm going to be talking about and dispelling some of those myths. I'm going to talk about two machines or two technologies that you see, and I would argue a little bit more frequently here in the Boston area, and also just I would say like in the headlines, these are just two technologies that I see a little bit more of. So just to familiarize yourself with what's out there. By no means are these the only two technologies that are in quantum computing, but just two, just so you can kind of get a sense of what's out there. And then I'm going to talk about 4 different roles that exist in the quantum space, 2 technical and 2 non-technical roles, and give you a sense of how to get in there. And at the end, I'm going to give you resources, and also we're going to go through how you can make use of those questions that you may have in this presentation to leverage them for employment. Okay, so the 3 myths. There are 3 primary myths that I hear a lot about when it comes to quantum is you need a PhD. There are plenty of roles that do not require a PhD. For some roles, yes, I want to be clear. But for the industry as a whole, no. Quantum computing companies need both those that do and do not have PhDs. And the same thing goes for you need to be a physicist. Physicists are certainly important, but they're one part of the larger equation. Quantum companies still need engineers, software teams, talent teams, sales, operations, finance, marketing, and so on. So do you need to be a physicist if you are in HR? Nope, you don't. The next here is that you need to master quantum mechanics. So here is that you need to really be a content expert. And what I'd say to that is you definitely have to have working understanding of quantum mechanics and quantum computing in general. You have to understand the underlying theory behind a lot of what you're going to be working in. But for the most part, you need to have a working knowledge of the vocabulary and just be able to be conversational in it. And for the most part, that can get you really, really far. Now, of course, if you want to get more technical, and if we talk about more technical roles, of course, you want to have more than just a working understanding of the vocabulary. But for the other non-technical functions, working vocabulary of what is quantum is sufficient. So I wanted to go through those myths first. Now, what is quantum computing? We talked a little bit about this, but again, just to kind of give a little primer. So with classical computers, we have ones and zeros, binary, ones and zeros. It's like a light switch. With quantum computing, we have what's called qubits. And so while quantum computers, when they're running, a qubit can be in a state where both outcomes are possible. So not both in like the mystical way, just a physical setup so that if we measure it, there's some chance we get a 0 and some chance we get a 1. And that's where superposition happens. So that's what superposition means. But when we're measuring it, the qubit has to answer like a regular bit. So it gives either ones or 0. So the trick is what happens before the measurement. So quantum algorithms arrange these possibilities so that bad answers tend to cancel out good answers and become more likely. So that canceling and reinforcing effect it's called interference. So think of waves in water or noise canceling headphones. Some waves add together, some waves cancel each other out. So the quantum computer is simply not just try to answer everything at once. It's more of a better way to say, if we run the programs and we look at the patterns, a better how do I say this? So like what's really happening here is that superposition and interference is more of a way to shift the odds towards more useful answers. I think that's like the better way to say it. And then running the programs many times and looking at the patterns are helpful ways to really look at how do we get more useful, more correct answers over time. So real money is being spent, and that money is being spent to solve real problems, like real life-changing problems. So what we're seeing here is that in quantum computing, the problems that could be solved are first drug discovery. So molecules by nature are quantum objects. So their electrons follow quantum rules, and regular computers, for the most part, approximate that, but the calculations get hard very quickly and get very complicated. And in some ways, classical computers just will not be able to answer the questions that we want in a reasonable timeline or even have the ability to even get close to where we want to go. So the hope is that quantum computers can help scientists model molecules more directly, screen candidates faster, and waste less time and on dead ends. So in theory, we can have drug discovery become a lot more cost effective, a lot quicker, and a lot safer for patients. So I also want to say too, is that doesn't mean that quantum magically cures diseases in the next year. The more honest version is more that it's a better simulation. We'll be able to simulate drug discovery in a better, richer way. The next is optimization. So what that means is that we're choosing the best option out of a huge number of other options. So delivery route spends, or it might sound like it's pretty simple. Like, you just go on Google Maps and you figure out like, okay, go to point A, point B. But when we start adding other factors like traffic, weather, time windows, capacity, inventory, things like that, at scale, it becomes very complicated very quickly. So regular computers already do some of this, like UPS Orion, great classical example. But when you have quantum computing, you're able to do this in a way that just surpasses anything that a classical computer can do, and you can get more richer, more in-depth data analysis than, again, like with classical computing, just because there's we're able to just get better outcomes here. So the third is cryptography. So some of today's securities depend on math problems that are hard for regular computers. So in theory, like when we get to a place where quantum computing is like commercially viable, available, we get error correction down. There's a thing where quantum computers will break classical encryption. And so that's going to be both like horrible, but also it's going to be a huge opportunity, because with that, we will find new ways to encrypt our systems. And so if you're thinking about like defense, there's a huge opportunity there for quantum computing to decrypt classical encryption methodologies and approaches. So this is a lot of reason why people talk about post-quantum cryptography. If we're just like going back to encryption. So it's right now, actually, sorry. So when we talk about encryption, you're probably hearing some of this conversation of post-quantum cryptography. And there are people who are already preparing for that world where quantum computing is going to just, disassemble, in a very, like saying that in an oversimplistic way, disassemble classical encryption. So those are things that are happening right now that people are really looking at, even with today's quantum computing technology as it is in its nascent form. People are looking into these different approaches and are spending real money in it and need people to help with these problems and solving these problems. So now I'm going to talk about the different technologies that are out there. So there are different types of quantum computing. So what I'm showing you here is superconducting. So with superconducting, I want to just first say a superconducting qubit is not a real atom. So it's a tiny electrical circuit printed on a chip. People sometimes call it artificial atom because when it's cold enough, the circuit can behave like a quantum system. So superconducting means that at very low temperatures, certain materials can carry electricity with almost no resistance. That property, though, is what makes these delicate quantum circuits really useful. The big catch is the temperature. So these chips run near absolute zero, as mentioned before. So that gold chandelier that you typically see when people talk about quantum computing, because a lot of times when they say quantum computing, the chandelier is the first thing that they always show, especially on TV. That chandelier, so what it's doing is it's making sure that the chip can run at like near absolute zero. And you can think of it as just like a very specialized freezer from quantum chip. This approach is important because it borrows from chip manufacturing, and the world already knows how to make these tiny circuits and test them and wire them and control them. That gives us superconducting systems like just a real head start. So now if we're talking about like jobs, if you're in cryogenics, semiconductor process, or even RF and microwave engineering for the controls for the electronics, these are skills that if you already have them, like you in theory could start relatively soon in a new job and start working in these technologies. So now we're talking about neutral atom. So neutral atom, we talked about Q-era. I'm definitely, in fact, if you look here on the vacuum chamber, so the thing on the left side of this, here on this card where it says vacuum chamber, that has the vacuum chamber component to it. This is technology from Q-era. There's also other companies that are using neutral atom, but since we're in the Cambridge area, that's kind of our the company that we tend to point to most. when it comes to neutral atoms, so it's a little bit almost like opposite philosophy here. Instead of making an artificial atom on a chip, you use real atoms as the qubits. So neutral atom means the atoms has no electrical charge or no net electrical charge. So real atoms of the same element are naturally identical. And so what happens here is that these atoms sit inside a sealed vacuum chamber. And the vacuum means most of the air has been removed, so stray air molecules like almost never really bump into the atoms. So instead of wiring every qubit, neutral atom system uses lasers. So it's a tightly focused laser beam that just acts like a tiny tweezer made of light. And that's why you will hear the phrase optical tweezers when talking about neutral atom. So the careful version of this, we talk about like room temperature, because sometimes like people will say like, oh, it's more like room temperature. The apparatus doesn't need a dilution refrigerator. The room and much of the hardware can be at room temperature. And the atoms themselves are still cooled with lasers, but you don't have that massive chandelier, right? The freezing, freezing a chip. So people are excited about this because of scaling. With superconducting systems, wiring becomes a big challenge, but with neutral atoms, you're steering light and arranging atoms in arrays, which can make it cleaner, and you can add more qubits without a lot of that clunkiness that you'd see with the chandelier. And so with folks who are interested in like this type of technology, it's like laser optics, it's semiconductor, it's prefab, the technical skills required for this, I would argue, are in some ways a little bit more accessible. And I think the industry has a little bit more talent for this because it's not requiring the type of specialization needed for superconducting. Okay, so inside Quantum Company, you have hardware builders, you have software engineers, you have talent recruiting, and sales and go-to-market. So these are the four. There are more roles in this, but these are four different roles that I want to cover with you all today. And with these roles, I want to share what's required and also how do you make your way in there. And you also talk through some of the skills that you probably already have. So the first is a hardware builder. So sub roles you would see: cryogenics engineer, RF microwave engineer, optical engineer, vacuum technologist, test and measurement engineer, process and fab technician. So skills that already transfer for these types of roles: reading data sheets, soldering, wiring, fixturing, lab notebooks, SOPs, like writing those, mechanical CAD, calibration, instrumentation, or calibrating machines, working in clean rooms. Like if you have any of those skills, working in hardware could be a path for you. And some of the industries that people are coming from to be in these spaces are semiconductors, working in semiconductor spaces, defense, aerospace, telecom, medical device, national labs, even university and research support. There are folks who have been working in quantum computing at MIT and even like not MIT, who have been getting experience in the hardware build and making their way into these companies. The next for sub roles, you would see like quantum compiler, algorithms engineer, error correction engineer, control systems software, SDK developers, cloud platform engineers. So the skills that you need to do this stuff: linear algebra, graph and theory and data structure, like knowing these types of things, understanding programming languages like Python, Rust, C++, having some sort of working knowledge of compilers and being able to compile software is huge, especially because when it comes to software, the software is being developed a lot of these companies are in some ways building the plane as they're flying, and they're developing their own compilers for their software. So if you can work in that space, there's a huge value add that you would bring to a quantum computing company. Distributed systems and reading academic papers, and I put slowly because these things are dense. So if you have that experience, you can make your way. I wouldn't say easily, but you can make your way as a software engineer. And again, where these industries are coming from: folks that are working in developer tools. So high performance and scientific computing. So if you're in any of that, there's a pathway in cloud and distributed systems, embedded control systems, graphics, game engines and simulation, quantitative finance and trading systems. It sounds counterintuitive, but there is a pathway in there. Talent recruiting, that's where I am. So roles you'd see like technical recruiters, university relations, executive searches, people ops, talent brand and community, recruiting coordinators. These are the types of roles you'd see. Skills that already transfer. Can you find people? Can you have a general understanding of the material? Do you need to know, O1 versus, square root of insert here, the square root of anything? No, you don't. Or square root of pi. You don't need that. It's helpful in terms of recruiting, and I would argue the recruiters that spend more time and become more technical and understand the material better and can understand the equations will do better. But is it necessary? No, but it is certainly more helpful. And so if you're coming into a space, coming into the recruit, or if you're a recruiter coming into the quantum space, you're from a lot of the industries that I'm seeing, it's semiconductor recruiting, biotech, defense, robotics, and even boutique technical search firms. If you're in those spaces, because you have that technical expertise, you can easily transfer in, and I do say easily, more easily transfer into a quantum computing company. And sales and go-to-market. So account execs, sales and solutions and sales engineers, business development, partnerships and alliances, customer success, product marketing. So really what you're doing is you're doing pilots, you're translating hardware specs, you're running technical sales cycles, you're negotiating, you're closing. Do you need to know the exact, again, do you need to know the equations? I'd argue no. But again, you do need to have a working understanding of the material so that you can speak to your clients, especially if they ask you questions. Now, you don't have to defend the methodology and the theory behind it, but you need to know enough to be helpful and supportive to your clients. And so where do you see these folks coming from? Enterprise B2B sales, SaaS sales, semiconductor and hardware sales, cloud, HPC, scientific instruments and lab equipment. So the instrument and lab equipment spaces, defense, and then deep techs and startups and business development. So 3 paths you can start next week. So you can start making your way into quantum. Contribute to a quantum SDK. It's open source. I should have put it, I will add in, if I haven't already, I think I do have one open source SDK. I'll go check. And if it's not there, everyone feel free to email me. Take a seat at the table. So there are industry programs. There are free programs that you can participate in. And I have a resource page for you all where you can sign up for them starting today. And then apply for the role that you already want. And even if you feel like you're not 100% qualified for it, I would argue you should still apply. Just practice and apply. So if you can code, do math, build hardware, there's already a quantum job waiting for you. And I'll say for the non-technical roles, if you can't do any of those things, there's still a role for you in quantum. Now, I will say there are 3 QR codes here. This is the hard part. What I'm going to ask you to do is, I'm going to start with the action item that I started off with. If you have a question today, instead of asking me, I know this might sound like, oh, come on, Arturo, do better. But there's a method to the madness. What I want you to do is I want you to scan the middle barcode where it says scan for QR's office hours. What I want you to do is I want you to update your LinkedIn profile, and I want you to scan for QEra. That brings you to the LinkedIn page for QEra, and follow them. Every month they have office hours. And what I want you to do is I want you to sign into their office hours and share your LinkedIn profile and ask for the LinkedIn profile for whoever's conducting those office hours. Build the relationship. The research shows that if you have a connection into a company, your chance of getting an interview goes up to 50%. If you have a director level person, your chance goes up to 91%. We want to build those relationships. And if you go into the office hours, you can get one-to-one FaceTime with a quantum scientist who can answer the most technical to the most basic questions you have. And this is literally why it's set up for these types of things. So I want you all to go to QR's office hours, speak to their team, build a relationship, and get your foot in the door. The next thing that you have here in these QR codes is if you scan here, scan for the full list, the one on the far left, those are a list of resources, free to paid training programs, certifications, and even a link to the SDK. Although, as I said, if for some reason it's not there, shoot me an email. Happy to be helpful and figure out why it's not there. To the far right is my job toolkit. So if you want to apply for a job, but you're feeling a little weak in the knees because you're saying, Arturo, I hear you. There's a lot of information here. You're making a great case for that. I may not be the most technical person, but there's a role for me. There is a free tool for you that will help you walk through your job application and reduce the angst for you to apply to your first quantum role. You cannot mess it up. So scan these, sign up for QEra's office hours, scan to get the resources, and scan to apply to get to the free career toolkit, and you can get your way, make your way into a quantum role starting today. I appreciate you all. Thank you for having me.